Okay, so good day everyone. So today I'm going to uh, describe and present a work about similarity learning, and the paper is Conditional Similarity Networks. This is a work that is published in the CVPR conference 2017. So let me start by an example. So let's say you are given a data set of fashion products, and you are asked to find the most similar items to a query fashion item. For example, like a green female short jeans. So you can see that this question can be confusing in the sense that you have so many criteria for to determine which are the similar items to the query items. For example, you can have different similar item according to the color. If you use the suggested gender as a criteria, then the answer will be different. Or if you use style as a criteria, then you will get different answers. So that is for human. So this question can be confusing. So how about for machine learning models or algorithms? So I want to talk about embedding and similarity search problem. So usually, as you may know, that feature embedding is a great way to learn the similarity measure between items or objects. And usually the embedding model based on a single similarity metric assumption, meaning that there is only one criteria to determine how two objects are similar. So in order to support multiple similarity metrics, then usually you need to change multiple systems. Okay, so what is this paper about? So this paper proposed a single neural network architecture that can handle multiple similarity metrics. So why this useful? You don't need to change multiple system anymore. And the second point about this paper is that a single architecture can outperform multiple networks that each chain for one similarity metric. So one thing, it has a single model from multiple similarity metrics, and that single architecture can outperform multiple networks that change for multiple criteria. Okay, so what is the so the context of this paper is that similarities. The assumption is that similarity is conditional, and it's conditional on some aspects. For example, you have three items here: the high heel, the T-shirt, and the sports shoe. If you use different aspects to compare the similarities between the three objects, then you can have different results. For example, if you use color as a reference, then you have the high heel and the T-shirt. They are similar, and they are different from the sports shoe because it has a red color. If you use categories, right, then the high heel and the sports shoe will belong to the same categories as compared to the T-shirt. But if you use like the occasion in which you wear the items together, then probably you will match the sports shoe and the T-shirt together. It's very usually strange to wear the T-shirt and the high heel, right? So that is to say that if you condition on different similarity criteria, you can have different comparisons in terms of how similar two objects are. So that is the context, and because you can have many similarity matrix. So you can also have multiple similarity observations. So this is the input for the model. Apart from the image, you also given a set of similarity comparisons. And the similarity comparison is represented in the form of a triplet that involving three images, xi, xj, and xk, and it is ordered in the form of the first item is a reference item, the second position is a more distant image, and the third one is a more similar image. So how to read this? This means that the third image is more similar to the first image as compared to the second image to the first image. So the first image is a reference, and the third one is a more similar image as compared to the second one. So you go back to this, right? If you take this T-shirt as a reference item, and if you use color as a criteria, then you will have the triplet, T-shirt, sports shoe, and high heel, because high heel has the same color as a T-shirt. So formally, you can represent this triplet comparison in as a form of triple with three index I, J, L, and C is a condition in which you use as a similarity criteria. So far clear? So this is the input and the observations. So what should be the output? So the output is you want to produce multiple embedding maps, and in this multiple embedding maps, each map represents one similarity criteria. So in this example, right, you have the fonts, and if you use a character type as a criteria, then all the D will be flocked together. All the X will be flocked together in the same area. But if you use the font style as a reference, as a criteria, then all the character with the same style will be in the same area, will be grouped together. So note that the embeddings are of the same objects. So meaning the object here and the object here are the same. But according to different similarity criteria, they will be in a different position in different map. And according to the type, then all the same characters will be in the same area. And according to the font style, then all the character with the same style will be grouped together. So that is an illustration of how the outputs should look like. So this is one example. Another example is that is fashion items. So if you use the type as a similarity criteria, then all the items of the same type should be close to each other and far away from other type. If you use a closure mechanism, then all the items with the same closure mechanism should be close together. So same set of objects, but different criteria will produce different map. So that's what we expect as output. So recall that is input, right? You have the similarity criteria, and then you have a set of comparisons, and the output should be like this: multiple maps for multiple criteria, and the embedding are of the same set of objects. So this is the overview of the architectures. So this is the input. So this is the image, right? And the next block is CNN network. So the CNN network will produce an embedding for each item, for each image, and they call this embedding is this rectangle embedding. And the next layer is what they call conditional mask. So this mask, the number of masks is the same as the number of criteria that you have to compare the images. So let's say you have 4 criteria, then you have 4 masks. You have 2 criteria, then you have 2 masks. And each mask for each criteria will produce one embedding map for the objects. So from here to here, right, it goes through a mask. So let's say if you use category as a criteria, then you use a category mask. And from this rectangle embedding, you go through category mask, you go to the embedding for the categories. So you see, this is the shared embedding for all the criteria, right? But after going through the mask, you can have a representation that make sure that the high heel and the sports shoe are more close to each other as compared to the t-shirt. The same mechanism applies for if you use for color as a criteria. It just that color will be a different mask, and after you apply the mask to the shared embedding, you get the embedding for the color. Any question for the architectures? Okay. So there is illustrations of how you can derive the condition-specific embedding from the initial embedding. So this is embedding produced by the CNN, and let's assume you have 3 criteria, which you have 3 masks here, and if you apply element-wise multiplication of the initial embedding and each of the 3 masks, you can have different result. And this is embedding according to the first criteria. This is embedding according to the second criteria, and this is embedding according to the third criteria. This is simply element-wise multiplication. So this is illustration of the previous masking mask, and the operation is element-wise multiplication.
What is 0, 1?
0, 1. No, this is an example. That let's say this is a mask for the first criteria. Then how do you derive the embedding of the object according to this criteria? You just multiply the embedding, initial embedding with the mask.
How do you know what's the mask factor? How do you know what's the mask factor?
So in the model, you will learn the mask. So the mask is parameter models, and you will learn the mask as well as the embedding of the images.
You mean it's supervised and so forth? They know
Yes.
what they expect?
Yes. Yes. So the input, we know what is a criteria, right? And according to this criteria, we have these comparisons. So yeah, note that we know the condition, we know the criteria in this problem. Okay, so how do we learn the embeddings? So conventional methods. So if you have a comparison of xi is more similar to xl as compared to xi to xj, then you expect the the distance between xi and xj to be greater than the distance between xi and xl. So the distance between the more distant objects will be greater than the distance between two similar objects. So the distance is basically defined as a L2 distance between the two embeddings.
H is some like threshold. H.
I think head is a parameter to prevent trivial
To be
solution.
learned.
No,
It's a fixed or to be learned.
I think it's fixed. I think it could be a epsilon value, so that it doesn't collapse to zero. So it is the example of learning the embedding from the original comparisons without the conditions. So here we don't see the condition, right? So let's say if we take into account the condition, then the distance between the images should take into account the mask as well. So you see the difference between the previous formula and this formula is that the embedding now will multiply with the mask. So this combination is embedding of the object according to this similarity criteria. So this one doesn't have the mask. This one you apply the mask to the embedding, and you expect that this one to be greater. The more dissimilar pairs will have greater distance as compared to the more similar pairs. Similar intuition, but just a different formulation. Like you take into account the mask in this case. Okay. So they also apply regularization to this rectangle embedding, and they also want to learn the mask so that they become the sparse vectors. They apply the L1 regularization to the mask. Okay, so that's about the architectures. Now let's move on to the experiments. So the data set that the paper used, they use two data sets. The first data set is a Fong's data set, in which they have two similarity criteria, the character type and the font style. I think the second data set is a fashion item data set. If I'm not wrong, then this one they have 4 different criteria. So this is an example of the 2 of them, but totally they have 4 criteria to derive the comparison. Okay, so comparative methods, they actually compare the models, the proposed model with 2 baselines. The first baseline is they don't have the mask. The second baseline is they don't have the mask, but they all learn from the same set of original comparisons. So let's say you have a comparison according to the color, you have comparison according to the categories, and in this model they just merge all the comparison together to become one pool of observation.
So it means there's no condition.
Yeah, there's no condition. So the second baseline, they have the condition, but they share multiple network, and each network exchange for one criteria. So let's say this one exchange for the color, this one exchange for the categories. So let's say if you have 4 criteria, then you have 4 networks, each change for one criteria. The third one is one of the variants of the proposed model, but they allocate the mask, they fix the position of the mask. So meaning that they fix let's say the first 10 position to be the mask for the color, the next 10 position for the categories, the next 10 position of the mask for the closing mechanism, and so on. So meaning they fix the position in which the mask will be learned for the criteria. Okay, and the last model is that they don't fix the mask; they just learn the mask according to the input and the objective function. Okay, so the first one, right? The first one, they don't have the mask. They just yeah. No, they don't have the mask, but they learn from all the Arduino chiplets they have. The second model, they learn from each chiplets of each criteria. And the third one is that they fix. Let's say they fix the first two for the first criteria, the second two for the second criteria, and so on. And the last model, they just learn it as it is. They don't have any allocation for the mask. So let's see the visualization of the mask that they learned. So in this case, right, this is a mask. If they don't learn of the first model, meaning they have one single mask only. Then you can see all the dimensions of the mask are equally important. If you disjoint the mask, then you can see the first criteria will only have non-zero value at the first 16th position, and the second criteria will have non-zero value at the next 16th position, and so on. Because you have 4 criteria, so it goes all the way to 64 position. And the last model, they learn the mask, then you can see only a few non-zero values for the mask for different criteria. So they did it expected because they use L1 regularization, so that the learned mask is actually sparse vector. So this is the result for the chiplet prediction task, and they only report the performance for one dataset, which is the fashion item dataset. So you can see, as compared to a single network that learns from all chiplets from all criteria, the proposed model is significantly better. If you compare to the set of multiple systems that change for different criteria, actually the margin is not really big, but it's still showing a better result in terms of the error rate for chiplet prediction task. So this figure is to see the performance of all the models when they vary the number of training examples. So the red one is CSN, the Conditional Similarity Network with the learned mask. So if you have only few examples to fit the algorithms, then the performance actually is not as good as if you change multiple system, which is the green one here. But blue one, sorry. But if you start to have more and more observation for each criteria, then the learned mask actually is showing better performance as compared to the multiple systems baseline. Okay, so in conclusion, right? So overall, this is a well-written paper, and the performance shows that there is small margin between the proposed models and the baseline that change multiple systems for multiple criteria. So I think because the margin is small. Oh yes. So the author should change the set of multiple networks, but with the mask, maybe because the performance gap is because the specialized networks, they don't have as many parameters as the proposed model. So if you change the multiple system with the mask, then maybe you can explain the performance gap. Okay, so also the author should be applauded because they released the implementation. All right, thank you very much. That's all.
Any quick clarification questions?